All right, better? Cool. So last time, you guys had a daily problem. You were trying to figure out what is the energy and the corresponding transition between a harmonic oscillator in the zero energy state and the high energy state, or a higher energy state. And it was a single oxygen atom attached to basically a metal surface. So you could think about it as like a ball and spring, where that's your spring, and you have a K constant associated with it. And we told you what that K constant was, or the frequency to make this vibration happen. That frequency was 1.800 times 10 to the minus or positive 13 hertz. Seem familiar?
Yep.
Yeah. Okay, so you guys had to look up what the energy is for a harmonic oscillator. So what did you find that energy to be? Like the general equation, if we have some principal quantum number n. We didn't get a chance to derive this yet, but
I used like 1/2 h bar v, something like that.
Yep, and there's a plus n in here. And if you remember from the reading, the different thing with this n is that you can have n actually equal to 0. So for the first lowest energy state, we have n is equal to 0. Oops, that's plenty of 0. That's a little bit better. For the third lowest energy state, what's n equal to then? So first is 0.
That was 1. I thought
1 will be the second lowest in energy. So that makes what the third lowest?
2.
Yep. We got 2. So if you calculate those, what you end up getting is 5.963 times 10 to the minus 21 joules. And if we're looking at E2, you get 2.982 times 10 to the negative 20 joules. Okay, so that tells us the energies, but how do we calculate the frequency, or the wavelength of light that we need to cause this transition to happen? So what do we know about the energy relationship? Like, how does that relate to frequency? Energy is equal to, what do we got? I can't see. Is John typing away? Well, way back when we first started, what's energy equal to, guys? You remember?
Like HV?
Yep, HV. So then we know that T is equal to D times lambda, right? So we can manipulate that. What's lambda going to be equal to then?
C over V.
Yep. So we plug that in here. At HC, whoops. We get HC over lambda, right? Okay, so now we can calculate a change in energy. C over lambda, like that. And now all we have to do is manipulate this around. Oops, except you guys can't see. There we go. All we have to do is manipulate this around, move E over to the other side, and we get HC delta E like that, right? And all we have to do is plug in some values. We get 6.626 times 10 to the minus 34 joules times seconds. What about the speed of light? What's the value of the speed of light?
3 times 10 to the 8.
Yeah.
0.998.
Yeah, I like that one a little bit better. More sig figs. Works out better for us. Times 10 to the positive 8 meters per second. And divided by the difference in that energy. If you calculate that difference, it ends up being 2.386 times 10 to the minus 20 joules. Okay, when we divide everything through, what are our units going to be?
Meters.
Yep, they're going to be meters. And you end up getting 8.326 times 10 to the minus 6 meters. Now, does that answer the question?
No.
No, what were we trying to get to? Or do you just assume that because I said, does that answer the question?
You
I
probably
assumed.
nanometers.
Yeah, we got to get into what unit again?
Nanometers.
Yeah, we got to get the nanometers. So for every 1 meter, how many nanometers?
1 times 10 to the 9th.
Yep. So in that case, we get 8,326 nanometers as our answer. Okay. So anybody have any real questions on that, or where did you run into problems?
I did that completely wrong.
Well, was it up here with the first lowest and third lowest energy state? Because in almost all cases, we've said in most of our quantum systems, n cannot equal 0, because if you look at that energy, you just end up getting 0. But for a particle in a harmonic oscillator, since we have this expression, n can actually be 0, and it still results in an energy value. So I'm guessing that's where you probably messed it up if you messed the problem up. Am I right?
Yep.
Okay. Don't worry, that's not a big deal. It'll be a little bit off, but not a ton. Okay. So that one pretty easy. We're going to figure out how we get to this energy expression, hopefully today. All right. So last time we found the first derivative of our system, right? Where we find the second derivative already, where we were looking at.
We're looking at the first and second, I thought.
Okay. So we already did the first derivative, right? Where we had f of x plus e minus alpha x squared times f prime of x, right? We did that one for sure.
We did, and then we did the second one as well.
Okay, so we found that result already, which was this big, long, complicated thing, what, e to the minus alpha x squared over 2 alpha squared x squared f of x minus alpha f of x minus 2 alpha x f prime x plus f double prime of x, right? Does that look familiar, or did we do something different?
No, that's what we got.
Okay, cool. So now what we're going to do is we're going to take this equation and we're going to solve it into that Schrodinger equation that we found earlier, where we manipulated everything to be equal to 0.
I don't know if I just wrote it down wrong, but I don't have that second alpha thing.
So this guy right here?
Yeah. After the minus alpha fx, I don't have that one in my notes. It's just everything without that.
Okay, so this thing is complete. I think we combined these terms.
Yeah, we did.
Okay, so we had like alpha squared x squared minus alpha, like in that fashion.
Yeah.
Okay.
Does that say negative alpha x squared over 2 connected to the e?
Yep, up here.
Yeah.
Yep, negative alpha x squared divided by 2.
Okay.
Is it too small on your screen? Should I write bigger?
No, it looks good.
No, it's
Okay.
fine.
Okay, so we ended up with that, right?
What did you say? I'm sorry.
What was that?
What did you say?
Is this, does that look right?
Yeah.
Okay. So now we have to take this and we want to try and plug it into our Schrodinger equation that we found earlier where we said everything was equal to 0. So we had, what was it, psi x squared like that. What else do we have? Plus 2me over h bar squared minus alpha squared x squared. That wave function equal to 0, like that, right? So what we're going to do, we're going to plug in for this because we figure these two are the same thing. Let's see what our expression looks like. It's going to look ugly and you're going to need a lot of space. So make sure you have some space. Okay. So we get e minus alpha x squared over 2. Plug in all this junk in. X squared. What do we got? Minus alpha f of x minus 2 alpha x f prime of x plus f double prime of x. And then we have plus 2me divided by h bar squared minus alpha squared x squared. And we have to multiply our wave function in here. And our original wave function was e to minus alpha x squared over 2 times f of x. Woo! And all that's equal to 0. Okay. Let's look for things that we can try and cancel out. We're going to multiply some stuff through, and we're going to see if anything can go away. So do you see anything that can be pulled out from this entire expression?
The 8 alpha x squared over 2.
Yeah, exactly. This guy right here, we're going to pull it out. And since it's 0 on that side, we can just get rid of it. So now what we end up with, I'm going to distribute the f of x's through because it's going to make our life a little bit easier. Get alpha squared x squared f of x minus alpha f of x minus 2 alpha x.
Can you move the paper up a little bit, please?
Oh, yep, sure. That better?
Yeah.
Okay. F prime plus f double prime of x plus 2me h bar times f x minus alpha squared x squared times f of x is equal to 0. Okay, so we end up with that expression. A lot to scramble down. Is there anything that can go away or cancels out at all? I know.
Yeah, I need a minute to write this down. I am so far behind.
That's okay.
What are you doing, Josh?
This is what I get for missing a class.
This part, the alpha x squared fx would cancel with the -1 at the end.
Yep, so this guy right here you're saying, and this guy
Doctor?
cancel each other
Like annotate the screen,
Yeah.
we could click it.
Wait, this?
Dr. Yule had it that we could like write on this.
Oh, okay, let's see. Ooh, that's fun. I'll figure that out.
Maddie, why'd you tell him that?
I know, now we're going to be doing this. Let's see. Meeting controls. Uh-oh, I don't have controls. Oh.
Maybe it was a picture that she posted. I don't know.
Oh, okay. You should be able to like go on the whiteboard and do things too. Oh, but you have a cool little writer thing. I got to figure out how to do this. Let's see.
The green shirt.
Sorry, Maddie's totally got me distracted. There we go.
Sorry.
Nope, it's okay. It's fun. Let's see. Multiple participants can share simultaneously. Sure. Advanced sharing options. I'll have to figure out how to do that. Can you do it like, can you share? You click the share button.
I don't know. She literally just opened like a page up and had everyone, we had to like all write something.
Maybe like this.
Yeah.
I am cool. Wow, I didn't think my handwriting could get any worse, but here we are. Can you guys edit that or do anything with that?
Yeah, we can.
Let's find out.
Draw a picture. Ah, there it is. There's something.
Wait, how are you writing?
So if you, I think you can go to the whiteboard and do it that way.
I think my touchscreen broke on my laptop recently, so I'm not going to be able to.
Oh, okay.
Excuses.
It's unfortunate. It's rough times.
Well, we know how to do it now. So we'll play around with that later.
I'm gonna pass the chalk to Josh.
This is some like weird D&D level stuff. Like I feel like we're so quiet compared to what we normally are.
No, we normally don't shut up. It's weird that we can't see each other. Can we see each other?
Yeah, I think you can. I see you guys like on the side. You see that?
John is MIA right now.
Yeah, John's stuff's not working. He can hear us, but he can't see us. Oh, no, he can see us, I mean, but we can't see him.
So I can insult him and he can't have a comeback.
Well, he can talk in the chat.
That's
Let's
what
see
you
what
like,
he's saying.
Sarah. You can definitely do that.
You're gonna get a private chat.
Oh, John can talk to everybody. He just said, "What's up" to everybody.
There he is.
He's throwing shade at you, John. I don't know.
Oh my God.
Okay, so we know we can cancel that guy out. And that guy out. Let's see what we get. We have an F double prime that doesn't have anything in front of it. Let's put that out front. There we go. -2 alpha x F prime x plus this. Okay, cool. Okay, and what do we know about these f functions? If you remember what we said f of x was, if you look back in your notes. Remember, I think it looked something like, what do we say? Do we say C is C0?
Yeah, C0 plus C of 1, X1 plus
Yep.
C2, X2 plus C3, X3, and so on.
Oh.
Like this, yep. And do you remember what that was called?
Taylor series? Or something?
Nope.
Power series.
That's what I
Power series. Power. It sounds cooler.
We were
Okay,
wondering,
so-
you know, guys.
So if we look at this function, we can describe this as a Riemann sum, summation to infinity, C sub n, x to the n, or C is equal to infinity. Oh, actually, we're going to start with, if we go to infinity, let's start with
Do
n.
X's have subscripts or superscripts?
Exponents.
That's oh, these, yeah, they
Yeah.
should be superscripts, my bad. Ruh-roh.
All right.
There we go. That looks better ish. So what about if we took, I don't know, let's say we took the first derivative of this guy.
What does will it telescope mean?
What's that?
What did you say, Maddie?
Said will it telescope? Look in the chat.
Will it telescope? Will it telescope? Calc 2. I'm not too sure what telescoping is, John.
What I'm talking about.
As
It's
an
an infinite series.
I don't think
I'm not too
telescope's a
sure.
mathematical term.
He said
Is
it's from part 2.
Telescope is a mathematical term. I've never heard that term. Well, maybe it'll telescope. I'll have to look that up and see what it is. When we're talking about f prime, though, we got to take the first derivative of this series here. What's going to happen to this term if we take a derivative with respect to x?
Become 1.
That becomes 0.
Yep, 0, because any constant is 0. What about that term?
Becomes what's it?
X.
1
Or
times.
just C1.
Yep, just C1, because we're taking derivative with respect to x. What about this term? Since it's x squared.
2 C2 x
Yep.
1.
Yep, x to the power of 1 or x. And then what about this next term?
Or 3.
3C3.
X
Yep.
squared.
Exactly, and it continues on that way. So let's try and find a way to express this. We're going to go to infinity, but where's our index going to start? Are we going to start at 0?
At 1.
Yeah, we'll start at 1 in this case. And then can you think of a function that would work out?
CN
Mhm.
2 minus n.
Would it
Well,
be
so
n?
up front would be like 2 minus n.
Isn't it times n minus
Or we
1?
know.
Yep, times n, and then we got that x.
Oh,
X is going to be what?
Minus 1.
Yep, n minus 1. There we go. But we can shift this whole thing over to 0. We could include 0 if we wanted to. It just means that that first term is 0. So we could do this if we really wanted. Right? It'll get us the exact same result. It just seems kind of dumb because that first term is going to be a 0. And why do we care about 0? Fortunately, in this class, we care about 0 a lot sometimes. So, all right. What about the second derivative then? First term right here, definitely still 0. Second term, what happens with this guy?
becomes 0.
Yep. Comes 0. And then, let's see, this term. What's this term going to become?
2 C2.
Yep. Plus next term.
Where
6
did the x go?
X.
Yep. 6C3 x. Yep. The x went away here because we had x to the power of 1. So if we take that derivative, that just ends up being 1, right?
Mm-hmm.
Let's do, yeah, and so on. It keeps repeating this way. Indexes, where are we going to start in this case?
N is 2.
Yep. Now, this one's a little bit trickier. We get n times n minus 1 Cn x to the n minus 2. And we can simplify that. It's also equivalent to this guy, where we start at n is equal to 0, we go to infinity, we get n plus 2 times n plus 1, Cn plus 2 x to the n. And that's where we just sort of shift everything. So those are equivalent to one another in mathematics. They've shown that to be true. Here, we're just going to run with that. Okay, so now we have this information. What we're going to do is we're going to sub this into the equation we previously had. So we'll keep that around and we'll bring that back in a little bit. Oh, where do we need it back?
Move it up for a minute.
Yep. That good?
Yeah.
Yeah, we're good.
Okay. Cool. So now we want to take this and we want to sub that back into this equation that we found up here. Let's do this. So, sub series into previous Schrodinger equation. Okay, so let's do that. Our first term, let's see. Off center. There we go. I need a level. What do we get? So we got some series. We set everything equal to n is equal to 0 because we want to start with the same index. We're going to infinity. We get n plus 2, n plus 1 times Cn plus 2 n. And that's for our first term, that f double prime. So this is f of x double prime, right? Okay. What else do we need? We need minus 2 alpha x f prime of x. So we got to have this minus sign 2 alpha x. And we have whatever we said for f prime. So the
Is
function
it part
that
of
we,
the series bracketed out?
yep. Oh, like why is this bracketed out?
So I mean, like you had the bracket right there. Is that going to go for the whole equation, or is that just part where the series is?
It goes for the whole equation.
Oh, okay.
Because this is all going to be, we're going to put in a couple of series. So like this part's a series, and then we have, what is it? We have
F1
plus 2me h bar squared minus alpha fx, like that, is equal to 0. So we're just plugging into this equation, and since this is a series, and that's a series, we can just pull the indexes out front if we start at the same point. Does that make sense, Josh?
Yeah.
Okay. Cool. So now what Maddie was telling us what goes here. What is it, Maddie? Or anybody?
For the 2 alpha x, since it's times f prime of x, would you do it nc of n minus 1?
Yep, exactly. nc of n x to the n minus 1, just like you said. Okay, plus now we need to have this junk minus alpha. Whoa, scared me. What's coming next here? So we need whatever the function was of f of x.
Just Cn xn.
Yep.
Does anyone else hear like dishes moving around?
Yeah. Someone's enjoying some cereal.
Moving dishes right now.
Multitasking. They're writing all this stuff down and they're cleaning dishes.
My dad's putting stuff in the dishwasher. He's right
That's it.
Hi, Mr. Wedvik.
It's okay, I'm a chemist.
Oh,
Hey,
Hey, there we go.
how's it going?
Sorry.
You missed PChem?
That's my favorite class.
Yeah. See, I told him it's all
It's
a good
Maddie's
class.
too.
I can't stop talking about it.
aw.
Oh. See, I told you guys. You'll look back fondly on these memories and be like, man, I miss doing second derivatives and stuff like that.
Yeah, she doesn't believe me how often Schrodinger's equation comes up in conversation.
Oh, I know. Or in your daily life, how are you going to know if you can tunnel through a doorway without it? I mean, okay. So we can find ways to simplify this expression along here. What can we pull out from all of this? Do you see anything?
Probably nothing.
So
Pull out an x sub xn. Maybe
Let's-
it's on there.
yeah, we can pull out xn's, but what about, we can do that easily from here, and we can do that easily from this series, but what about here? Why can we pull an x to the n out?
Because x to the n minus 1 is just x to the n times x to the negative 1.
Wouldn't it cancel with x1?
x1, yeah, so this guy right here,
Yeah.
so that one and that one, if we combine those together, if we have x times x, x to the n minus 1, what's that equal to?
X to the n.
X to the n.
Yeah. So really, we have an x to the n that we can pull out from all of this stuff. So n is equal to 0, going to infinity. We can pull that x to the n out of this expression. Minus 2 alpha x. Oh, no, x there, sorry. Times n times cn plus 2me over h bar squared minus alpha cn x to the n all out front. Okay. So now what we need to do is we got to figure out these coefficients. If we figure out these coefficients, we'll know everything there is about this equation. So now we need to figure out Cn plus 2 and Cn. Okay, so we have an expression, and if you solve this thing, we can get rid of that x sub n, and we can have everything in terms of Cn, which looks like this, plus 1, Cn plus 2. Basically, it's all this stuff, but we've ditched this over to 0. We end up with alpha n c sub n plus 2me h bar squared minus alpha cn is all equal to 0. So now what we're going to do is we're going to take this and we're going to solve for Cn plus 2. Okay, does anybody really want to go through all the nitty-gritty mathematics to show how that comes about?
No,
Anybody?
not really.
No, not really.
So why did you get rid of the series part? Why are we just getting rid of that in the xn?
So we are getting rid of the series part because we're just trying to find an expression for the c sub n that works. The series can still technically be here, but it just makes this look more complicated. What we're going to find is that this expression here is a recursion relationship. Did you guys ever talk about recursion relationships in like Calc 2 or Calc 3?
I don't think so.
Okay.
I honestly don't remember. Yeah.
Yeah, it might have been a while. Basically, what happens is there is just a what do you call it? Like, what are they? There's a pattern, a reoccurring pattern that just keeps showing up over and over again with this mathematics. So it just keeps popping back up and up again. And the relationship that we have for this system divided by n plus 2 n plus 1 c to the n. And this is a recursion relationship. Okay, and the cool thing about this function is, or what I think is cool about it, is that it follows rules based upon if the coefficients are even or if they're odd. So therefore, this expression right here, it only depends, only c sub 0 and c sub 1 need to be known to get any value, any of these c sub n's. Okay. So in order to get these, if we know c sub 0, we have to know c sub 0 to get all even. Coefficients. And if we know C1, we have to know that to get all odd. So as an example, if we wanted to know, let's say C532, what coefficient do we have to know to solve for that?
C0.
Yeah, we have to know C0. Could you give me an example of one where we'd have to know C1?
531.
Okay. Very creative.
Yeah.
Cool. Okay. So now, oh, am I okay to move this?
Now you are.
I'm good?
Yep.
Okay. All right, so now the problem is we need psi to be bound. So in order for our wave function to be bound, and not infinite at any value, at some value of n, this value, Cn plus 2, must be 0.
That n of j.
This is,
Here's a comma.
oh, that's a comma. So it works out that Cn plus 2 must be 0. Therefore, the expression, this expression that we had previously, this guy, this whole side's going to be equal to 0. So we get 0 is equal to alpha plus 2 alpha n minus 2me h bar squared Cn for n plus 2 n plus 1. The other important thing is we know that C sub n, n plus 2, and n plus 1, they do not equal 0. Now what we can do is we can move this stuff. We can just shuffle that over to the side with 0, and we're left over with this expression. Alpha plus 2 alpha n minus 2me h bar squared is equal to 0. Oh, we have equal to 0 on both sides for some reason though. Okay, now this is where things, we've taken a really complex system and we've distilled it down to something really simple. Do you remember what this alpha was? Because we want to try and solve for terms back to the variables that we had. What do we define? Oops. Time
Was
for
it
you to
2
shut up.
pi VM over h bar?
Yep. 2 pi frequency m over h bar. So let's plug that into here. And we get 0 is equal to 2 pi e m h bar plus 2 n 2 pi v m over h bar, and this just hangs around.
And go away.
N is right here. We just pulled out, we just plugged in for that. Does that make sense?
Mhm.
All right, now the goal of this is we want to solve for E. So what would you do to solve for E?
Multiply everything by h bar squared.
Yeah, if we multiply everything by h bar squared, we're going to get rid of that stuff, right? So we get 2mv h bar plus 2n 2 pi vm h minus 2me, right? Anything else? We're trying to solve for E now.
You can move everything to the other side and then
Yeah,
divide
we're going to
by-
move just this guy to the other side. So we get 2me pi vm h bar plus 2n 2 pi vm h bar, like that, right? Okay, anything else you can see to make this a bit simpler?
You can get rid of some 2's.
Yep, get rid of some 2's. Is that it?
Well, I guess you got to move the m over as well.
Yeah, we can get rid of the m also.
M.
We're going to ditch that m and we get 2, oh, never mind, pi v h bar plus 2n pi v h bar. Okay, if you remember, what's h bar again?
It's a h over 2 pi.
Yep, h over 2 pi. So now what we can do is if we have h bar times 2 pi, what's that equal to?
Just h.
Yeah, so now we got a bunch of h's in here. We can pull out that pi and make this a bit simpler. What happens is this becomes 1/2 VH. This term becomes VHN. So now what can we do with this part of the expression?
Out the h's.
Yep, pull out h's. What else can we pull out?
Frequency.
Yep. And we're left over with VH 1/2 plus N. And hey, I think you guys used that in your last daily problem. So that's where that expression comes from. And the reason we can go N is equal to 0, if we look back at our series, we started with our index being 0. So that's why N can start at 0 in this case, compared to other quantum systems, but that couldn't happen fast. Okay, I think that's about all the time that we have right now. I'm going to quit recording, but do you guys have any questions at all?